to fit into either two weight classes. It needs to fit into a under 4 kilograms mass weight class or the 1.5 kilograms mass weight class. The Knight is in the under 4 kilograms mass weight class, and then the walking robot that we will discuss at the end of the presentation is in the 1.5 kilograms mass weight class.
The original design that the robotics team started with was named Ant, and Ant was supposed to move forward by using its legs. The design used a chain and gear system in order to run 3 legs at the same time, with one motor on each side driving the right versus the left side. The turning of the robot would have been achieved by making the legs run in opposite directions, so the robot would theoretically turn 360 degrees without ever moving forward or backward. This is a short video of a prototype of Ant. Now, the original leg-based design was retired for practicality purposes. The legs themselves acted as levers with a mechanical disadvantage on the side of the motors. When the feet would hit the ground, this caused immense amounts of torque that it took for the motors to overcome in order to move the legs in any sort of way. This could not be solved even with the addition of extremely imbalanced gear ratios. Now, there were certainly ways to fix it, such as different gear ratios or different motors. However, the amount of time, money, and advancements that the team would have had to contribute to an uncertain project made the entire design unviable.
For the final robots design, we decided to utilize successful aspects from robots we've built in previous years. However successful previous robots were, we chose to construct the final robot with new advancements to achieve a much smaller and lighter build without compromising its technologies that have aided in our past successes. Some of the aspects taken from previous robots include the ramped front infrared sensors, the basic sensor integration, and the basic shape of previous wheels, which allow us to easily conquer obstacles. To reduce the robot's size by 1.5 inches, we chose to offset the motor placement, allowing them to sit in front and back of each other rather than side by side one another. We also switched from a double width chain system to a single width chain system. This allowed for another 1.5 inches, or for another inch to be taken from the robot's width and size. In previous robots, we used a wheel that had a solid side with the other side being sunken in. This year, we decided to sink both sides of the wheel in and use a spacer to keep the wheels away from the body. By doing this, we were again able to reduce the robot's overall weight due to our ability to use less plastic than our previous model. This is the basic design we began with for our improved design. You can see the offsetting of the motors, decreased space for the chain system, along with how the general placement of the wheels corresponds with the body. Overall, we lost a total of 1 kilogram in weight from last year's design. We went from roughly 4 kilograms to roughly 3 kilograms.
Another way we reduced weight is by 3D printing our sensor mounts and wheels. The 3D design team has focused primarily on designing these sensor mounts and the design of the legs for our numerous prototypes of leg-based robots.
This was our final board design for the robot and its variety of components. First was the propeller chip, Second is the tilt sensor. Third is the EEPROM. Fourth is the 3.3 volt regulator. Five is the 5-volt regulator. Six is the compass pins. Seven is the OLED display screen pins. 8 is the A to D converter. 9 is a variety of resistors. 10 is the capacitors. 11 is the 3-pin headers, which connect to a variety of sensors. 12 is the prop plug. 13 is the crystal. 14 is the button. And 15 is the power plugins.
This is our electrical block diagram for the final version of our board. As you can see here, it starts with a 12-volt battery, which gets put through a fuse and converted to 9, 5, and 3.3 volts respectively. 9-volt power powers both motor controls and the motors, while the 5 and 3.3 volts powers the components located on the board. We have data inputs and outputs. The inputs are labeled in black and the outputs are labeled in blue.
The current robot uses a variety of sensors to gather information about its environment, including ultrasonic distance sensors, which Parallax calls pings, used as the main head-on detection sensor, as well as microswitches as a physical bump sensor to detect anything the pings miss. We have infrared sensors to detect pits before the robot falls into one, and a compass to determine what general direction the robot is facing. We also have an accelerometer as a tilt sensor and an OLED display to print out any sensor readings and other information that was useful when debugging the program. The robot uses a Parallax branded microcontroller, which has 8 cores, or cogs as Parallax calls them, available to run parts of the program in parallel and thus faster than if it could only do one thing at a time. The program makes decisions based on sensor input in order to first detect and avoid any pits and obstacles. And then once the path is clear, it'll orient itself so the compass is facing north, although the compass can be rotated to make the actual robot follow any desired course. The program was developed in a subsystem manner, where each sensor was individually tested before first integrating it into a separate driving program to determine how the robot handles the input, and then into the main large program that incorporates everything that we had gotten working so far. And we did it this way in order to reduce the number of large drastic changes, as well as have a baseline of what we know already works to make it easier to debug the program and fix any glitches.
So here's another facet of our subsystem testing, which is the testing of our robot indoors. So every time that we made an adjustment to our code or tested a new thing on the robot, we would first test it indoors, and then if it worked from there, it was taken outside in order to be tested in our sandbox. So here's the robot moving, avoiding walls indoors. You know, as with everything that we do here, we're going to have in testing, we're going to have some failures, and so every time that we tested something, things didn't quite go right or exactly as planned, and so therefore, we had some failures, and we would have to make small minor adjustments to our design or our code based on these testing inputs that we had. Here is probably the most spectacular failure of the robot face planting into the pit in which it should have avoided. So now we're going to highlight some of the testing successes of each of the parts of our sensor inputs. So first is our pings, or ultrasonic distance sensors, avoiding walls. As you can see, the robot is moving away from these walls based on the input from the pings, which are the little eyeball-looking things above the pink paddles. And now here is the bump sensor testing. Here is the robot slamming into the wall using the pink paddles that are connected to micro switches and are avoiding that obstacle because it detected that. Now here's the integrated part of the robot, which is the integration of the different sensors into a larger program. And here we have the compass and the pings working in tandem, avoiding an obstacle with the pings and then using the compass to orient itself towards the direction that it wants to go. And now here's a successful IR testing run where it does not face plant into the pit. It actually avoids it. So because we have had such great successes in testing, we believe the team believes that the Knight should be able to withstand the various challenges that we do associated with taking it to the sand dunes, which we will be doing this summer. Now we're going to talk a little bit about the walking robot.
So we decided not to completely give up on a walking design. We decided to make a second robot in the lower 1.5 kilogram weight limit. The new design uses a much simpler walking motion. It uses one motor for forward and backward motion and one linear actuator for turning. I currently have the walking robot with me at home, and I'm working on designing feet for the robot. I think we have a video here, but it might not play very well, of some of the robot's first steps. So originally we used a chain mechanism to control the legs, but we now use gears because the chain had problems with binding and fighting against the legs. We hope to migrate a lot of the programming from Knight over to the new robot once we have finished all the testing with the motion of the robot.
So just in conclusion, we'd like to give a big thank you to our two head advisors, Ms. Cindy Clements and Mr. Earl Nesbitt, for all of their support with TSJC Robotics, advising us and pushing us to make sure that our robot works, or two robots work just as good as they are now. And our big sponsor, Parallax Incorporated, and then all the rest of the people who support TSJC Robotics. I guess it opens it up to questions.
So you'll have to raise your hand if you would like to ask a question. You can do that underneath the participants window if you scroll along either the top or the bottom of your screen. Or I could just try unmuting everybody and see if there's a question, since I don't see any. Oh, there's a. I'll try it for just a second, just in case someone isn't finding the raise hands button. So all of you are unmuted.
You're up right now.
So any.
You're bad.
Wait, you went to bed at 21?
Probably.
Okay, so the other team, is Emma with us?
Yes,
Christy?
Emma has joined.
Okay. So do you guys want to share your screen? I'm not sure who's sharing.